In this demo, we will demonstrate how the FedL, Federated Learning component of the Marl project works. In order to do so, we will describe the client part of the component and the server part of the component. The FedL component is based on the Flower Python framework, which is used for federated learning, and the client part of our FedL component consists of a wrapper class, which is used to wrap around the model that we are using in order for it to communicate with the federated learning server and share its parameters with other clients in this process. So for these purposes, on the client side, we are using the audiovisual crowd counting model that we received from Arcus University, and we have written this wrapper class around it, which is used for parameter sharing with the federated learning server. In addition to parameter sharing methods, we also need to define some specific methods that share some additional data that is required for our non-uniform sampling strategy that we will describe a little bit later. For example, we need to define how the model gradient norm is calculated, which is an important parameter for the non-uniform sampling strategy selection, client selection process. And this information needs to be shared with any model update that this model will provide. In addition to this, we also define some specific methods that are used to obtain parameters of the underlying model, and also a definition how this model should be trained and what data or parameters needs to be shared. As with other federated learning strategies and processes, data never leaves its client. Only the parameters of the model or the weights of the model are shared between federated learning clients and the federated learning server. So for example, here in the fit method, we can also see what parameters are shared. So we share the model weights, we share how many examples that did this model use to obtain these weights or parameters. We also provide some meta information, for example, how long the training process was, and also some inner parameters of the model, for example, batch size or the mentioned gradient norm is sent to the federated learning server. On the other side, on the server side, we have our non-uniform sampling strategy, which main purpose is to allow for flaky communication updates. So for example, we can have some rounds of federated learning process where some clients are unavailable or inactive, or we are simply skipping them based on some rules that we have defined. So in the non-uniform sampling strategy, we use all the parameters that the client has sent, that we mentioned, for example, how many examples, what is the gradient norm, to decide whether this client update is, let's say, interesting enough to include in the global model that we are building. So we have modeled a stochastic process which is designed to select only those clients from which we need to accept the updates and which will benefit the global model. So here is the implementation. We will not go too much into details here, but rather I think it's better that we show some experimental results with this strategy. So the baseline for our experiments is the federated averaging, which is the most widely used strategy for federated learning. And we can see here that with random splitting of the data between clients, we can achieve similar client accuracy both for the federated averaging strategy and for our non-uniform sampling strategy. We can also see an interesting part of the experiment that we did, which is client starvation, which is basically when some clients do not receive any new data that they can use for training, what happens in those situations. And we can see that the global model that we are building with other clients also helps these clients that are starved of data by sharing parameters with the other clients. Another experiment which is also very important, and as we mentioned, the idea behind the non-uniform sampling strategy is if we have, for example, flaky communication, so we want to minimize the data usage or the data transfer sizes, let's say, in these situations. So we can see here that when compared to the federated averaging, which has constant, let's say, data flow, we can achieve similar accuracy with less amounts of data transferred between clients and the server. So the red line is the non-uniform sampling strategy, and the blue line is the federated averaging strategy. We also tested, so the previous experiments, or I didn't mention this, were for the PyTorch model for the basic NIST dataset. We also tested with some more complex datasets, for example with FMNIST, where we see very similar results, but the difference in data transfer size is even greater, because if you use a larger model, the parameters that are shared will also be larger, and then our strategy makes scenarios like these even more beneficial, because the parameters that are shared need to be shared less often, and therefore we have less data flow. Again, accuracy is very similar. We again have some starvation of some clients which do not have enough data, but these clients also manage to learn with the data or the model updates from other clients.